Okay, we are looking at example 2A on page 96 of the workbook. This is asking us to determine whether the series that we're given here in part A converges or diverges. And this is the first type of example where we're not really told which convergence test to use here. We have to decide for ourselves. That's a bit of a challenge at first because we've got so many different convergence tests to choose from. So hopefully by this point, you have a copy of the handout that's been sent to you, the one that gives you kind of a summary of series convergence tests. And on one side of the handout, there's a flow chart that sort of gives us a possible order of tests that we could go through, kind of go down a list and figure out which convergence test is going to work for us. Okay, so we're going to try to use that method on this problem, sort of go down that list and see if we can arrive at a convergence test that will allow us to answer this question. Okay, so if we start with the test for divergence, that is very high on our list because if it works, it's not a difficult test to do. Okay, so I always like to start there and ask the question, might that work for us? Okay, let's try it. So the test for divergence works by just taking the limit as n goes to infinity of the nth term of our series. Okay, we're going to need to use L'Hopital's rule to take this limit because it has the form infinity over infinity. So take the derivative on the top, we get 4n, and on the bottom, 12n cubed. Notice that we can do a little simplifying. So there's an n in the top that cancels. So if you cancel the n into the n cubed, you're going to get 4 over 12n squared. And notice that that limit is going to be 0. So what does that tell us if we get a limit of 0 in the test for divergence? Well, unfortunately, that means that the test is inconclusive. Okay, so this test didn't work for us. And that's okay. It just means that we have to try a different test. Keep going down our list. Okay, and kind of next on the list is the ratio test. Would that work? Well, unfortunately, that's not going to work either because the ratio test, to use it successfully, we need to see one of two things in our series, either a factorial, which we don't have, or a constant raised to the nth power. And we don't have that either. We've got n's raised to constant powers, like n squared and n to the fourth, but we don't have any constants raised to the nth power. So the ratio test is also not going to work. Moving down our list a little bit farther, we come to the limit comparison test. Maybe that'll work. Okay, let's try that out. Okay, and you might recall that kind of works by starting, okay, with the term in your series and looking for dominant terms. Okay, so if you look at the top and the bottom of your fraction, the dominant thing in the top is the n squared. That's the thing that's growing the fastest. And then the bottom is the n to the fourth. That's growing the fastest. All right, cancel the n squared into the n to the fourth, and this breaks down to just 1 over n squared. That's the term of the series we want to compare to. All right, so what kind of a series is that? 1 over n squared. Notice that it's a p series with p equal to 2. P is just the name for the exponent again. And because that 2 is greater than 1, this is a convergent p series. Okay. And so, to actually execute this test, we need to take a limit. Okay, and remember, it's the limit of bn over an. Let's remind ourselves what those two things are. So bn was our name, okay, for the series that we were given, and an was our name for the term in the series that we're comparing to. Okay, so we just need to take the limit as n goes to infinity of the bn over an. Okay, we need to divide by an, which is the same as multiplying by the reciprocal of an, which is n squared over 1. Okay, there's the limit that we need to calculate. All right, so let's first do a little algebra. We can take that n squared and multiply it through the numerator. 2n to the fourth minus n squared. And on the bottom, 3 n to the fourth plus 2. Okay, now we could use L'Hopital's rule on this limit. That would work just fine. But I can tell you that we would have to do a couple of iterations of L'Hopital's rule. It would be quite a bit of writing because of the fact that we've got a pretty complicated expression. So I'm going to fall back on the alternative to L'Hopital's rule. We talked about this way back in the section on sequences. Okay, I believe we called it the dominant terms method. What we did there was we sort of identified the thing in the denominator that's growing the fastest. That would be n to the fourth. And we multiplied the top and the bottom of our entire fraction by 1 over that. Okay, that has the effect of basically taking every term and just dividing it by n to the fourth. Okay, so if we take every single term and just divide it by n to the fourth, here's what we're going to get. We'll just do that term by term. Okay, continue down to the next line here. And that looks a little bit ugly, but again, there's a lot of cancellation that happens. You might notice that those n to the fourths go away and give us just a 2 and a 3. And then the other two fractions, n squared over n to the fourth. Okay, if you do a little cancellation there, you're just going to get 1 over n squared. Okay, and then moving down to the bottom, 2 over n to the fourth, not really anything that we can do with that. Just leave it the way it is. Okay, and what's nice about this way of writing it is we can ask the question, what happens as n goes to infinity? Well, notice that these two fractions, those are both going to go to 0 as n gets big. Okay, and so what do we get in the limit? Well, those two circled pieces are going to disappear, and we get a 2/3. That's the value of c in the limit comparison test. And notice that it's positive and finite. That's what we want. Okay, so we've basically convinced ourselves that the limit comparison test is going to work. All that's left is to write the proof now. Okay, and this is going to sound the same as the previous two that we already wrote. So we'll start by mentioning that we calculated a c and got a positive and finite number. Okay, next thing that's important is to notice that the AN series, way back up here, was a convergent series. Okay, a convergent P series, P equals 2. As a result of those two facts, we can conclude that our given series also converges. Okay, by the limit comparison test. All right, and limit comparison test, that's kind of long to write out, so I like to abbreviate that LCT. That just stands for limit comparison test. Okay, and notice, basically the idea of this test again is that however the comparison series, the 1 over n squared, behaves, that's the way that our given series is going to behave as well.